Hi, this is a video made as part of the Distributed Systems project, our project of distributed Bitcoin miner, project number 34, and teammates you can see here. And the contents covered as follows, starting with introduction. Like a database, Bitcoin needs a collection of computers to store its blockchain. For Bitcoin, this blockchain is just a specific type of database that stores every Bitcoin transaction ever made. In Bitcoin's case, and unlike most databases, these computers are not all under one roof, and each computer is a group of computers operated by individual, a group of individuals. What is blockchain? Blockchain is a specific type of database. It differs from a typical database in the way it stores information. Blockchains store data in blocks that are chained together. Hash functions generated fixed length fingerprint for an arbitrary length message. Here, the basic properties simplify hash function logic. Cryptocurrency is a medium of exchange like normal currencies such as USD, but designed for the purpose of exchanging digital information through a process made possible by certain principles of cryptography. It's an encrypted digital currency. Cryptography is used to secure transactions. Bitcoin is a decentralized digital currency. Bitcoin concepts. Dual. Typical Bitcoin looks like this. You can see the picture. Mining. Bitcoin mining is well secured as it is a decentralized currency. It makes decisions depending on consensus. Bitcoin miners validate every transaction. Bitcoin reward is the amount that is given to the miner in form of reward for every new Bitcoin created with each block mined and added to the blockchain. There is no limitation in Bitcoin mining, other types of Bitcoin mining hardware. Technicalities of a Bitcoin miner. A Bitcoin miner will have to join a Bitcoin network and connect to other nodes. Once it's connected, there are 6 tasks to perform. Listen for transactions, maintain blockchain, listen for new blocks, assemble a candidate block, find a nonce that makes your block valid, hope your block is accepted, and drop it. Here are the descriptions of these 6 tasks. And next continues algorithm and code analysis, code output, and all those.
Okay, so I will be explaining the algorithm. So in a sequential Bitcoin miner, in a simplistic way, so what the input is 2 values. One is the block data and another one is the target. Okay, so we will, in a sequential algo, what we do is we iterate the nonce values from 0 till some function output is less than the target. Okay, so what is this function is it is the in this function we will combine the nonce with the block. We will do a simple addition, then we will take the hash of the addition. So we can in a real Bitcoin mining we use double shower. So but now here we are using MD5 hashing, and with that and that output value should be less than the target. Then only that nonce we found that nonce like it is an invalid nonce, or else we will check the next value. Okay, so this is a sequential algo. Coming to the implementation of it in a distributed manner. So what are the challenges and how we implement this? Okay, so let's say initially end process started the system. Okay, so one of them has to be the coordinator in that system. Okay, so to elect the coordinator, we are using leader election Bully algorithm. So what does this, like every process has an ID and every process knows other process IDs. Okay, so so once the system is started, so now we will be like the election, like as the process with lowest node ID. So in actually the Bully algorithm takes the highest node ID, but we made some modifications so that the lowest node ID will get the process. Okay, so we'll get the coordination. Okay, so one process is elected at the root. So let's say it is the P0. Okay, so let's say P0 is the root process. Then so once the root process is selected, so what this root process does is it will start assigning the values to the other process for the to compute. Okay, so the values are go with this formula. Okay, so every process Pi gets I minus 1 into k. This k is a metric, so like we'll It is different for different clients depending on it depends on the computation, the network latency. By that we will choose K. Typically this K in our example we chose it as 1 billion. Okay, so what this says is number of values a process gets in a single run. Okay, yeah, so we will send the initial value. So let's say I to be process 1. Okay, let's say for example we take the process 1, then will send the values 0 to K and this step. This step indicates like after how many values should the process update the root process with the status. Okay, so let's say K is 1 billion. Okay, so and the initial value will be 0. So 0 to 1 billion. So the process 0 sends P1 0 to 1 billion and with a step value of let's say 10 power 6. So means a million. So the process computes every million, and then it sends to the parent process that I have completed this million. Okay, and it computes next million, and it computes and sends the parent process that I have completed this million. Like I have computed up to 2 million. Okay, like this process going up to the last value, that is billion. So once the process finishes, it will send the finish message to the root process. So and the root process will send the will send the next set of values to the process to compute. So if the process finds the nonce, then it will send a found message attached with the nonce value to the root process. So the nonce process sends other processes to abort. Okay, yeah. So what we included here is the node additions. Okay, so whenever a node is added, this algo is made such that node additions, removal and failures are like it can manage it easily. Okay, so whenever a node is added, a process like it knows which set of values are assigned to which and which setters are remaining. So it will assign from that pool to the new process whenever a node is added. And whenever a node is deleted, whenever the node is failed, so this process actually in the update status messages, when the root process don't get a status message from the child processes within a specified time, let's say some 2 minutes or 5 minutes, then this process the root process sends a message to the query message to the process. Let's say P1 is not so if it gets a reply message, then okay, the process is working fine. But if it doesn't get reply message, then we assume that the process is failed. Okay, so as the process is failed, already we have the status value before, like the process P1 sent before. So up to that status, so nonce is not found, so we don't need to compute the nonce again. Okay, so and we only compute up to from the status to the to the K value it assigned to. Okay, yeah. So that's the basic overview of the algorithm. And one more thing, like whenever the root process fails, then a Boolean algorithm will learn and make sure root has a coordinator will be there. Okay, yeah. So this is the overview of the algo. Now we will show you some demo of the code. Okay, so during the implementation, due to the limitations of MPI, it can't handle the remote execution. So we wanted to implement till node additions, deletions, handling the node failures, and so we also want to do remote execution. So there are 5 members in our team. So we want to use our remote laptops, and so that the computation is done in every other laptop remotely. So utilizing the distributed full power. But due to the limitations of MPI, so we couldn't do that. So actually we have done two codes basically. So one is for the MPI and one is for the remote Bitcoin connection. Remote Bitcoin miner. So the first will run only in locally with a fixed number of process, which is from the MPI, and the second thing, so it runs remotely with some with the resource sitting at the server, and this child processes will connect to the server and get the values, and the it is kept synchronized so that no two processes get the same values and all. Okay, so it keeps so that we can take full advantage of distributed systems. Now we will show a demo of how we will do it from different pieces, and we are staying in different places of our code.
Okay, so here you can see that three processes are running from different systems. They are connected remotely. um, so the first process started, got the values from 1 to second billion, and this second node, it got from 0 to first billion, and this got from 2 to 2 billion, 2 to 3 billion, sorry. Okay, so let's see in which process do we get the nonce. Okay, so these are connected remotely. Okay, uh, so one disadvantage with this remote is that the process cannot communicate directly, so they need to go with some media, so which we use the Firebase as it, and we implemented locks and critical locks, so that like no two processes have the same node values and all. Okay, yeah, okay, so I think
Okay, so now I am going to show how the node additions and deletions are. So let me run the first process. So executing the file. So the first process has started and we got the value 0 to 9. So the node additions. So let's say we had one more process by just executing and this file got the values from 2 to 9. Okay, so this is how the node additions are done. And so let's say this process, the second process, it failed due to some error. Okay, so here we kill the process, so it failed, so you can see that the process is failed. So let's say now this needs to be handled, right? This values needs to be taken care by a different process. Okay, so when we will run here this file, so now this process will get the we stopped it here at 10th 1 billion with the 3 million. So and here it starts from this value. Okay, so that's how the node failures are handled, and at any point the node can exit. Okay, it just fails basically, and the next process continues. Okay, so let's say in this process we will start the fourth process with and this process it starts from 2 billion to 3 billion. Okay, so that's how the value goes, and the node additions deletions are fine. Okay, so for this we use logs and all, so that when multiple clients execute at once, such that same process two processes doesn't get the same values. Okay, so we use logs to synchronize and all. So we use transactions, Firebase transactions, and to maintain it all. Okay, so that's it.
So now let's try to look at the output analysis. So we can observe two trends from this graph. So the first trend is, as the target value decreases for a particular n, the time taken to find a nonce increases. And the second trend is, as n increases for a given target value, the time taken to find a nonce decreases. So this is the graph that consists of all the target values and the various n. And for the second graph, what we can observe is that as the target value decreases, we can find that it gets more difficult to find the nonce value. So yeah, that's what happens. And yeah, so we also need to tune k and step parameters further and for different lines. The factors that are need to be considered are network latency, computation speed of device. So client libraries need to be tuned according to the device.